Welcome back to Unit 2.4 Alkenes, and in this video we are going to address the 9th point of the specification for this topic, point 2.4.9. And it's again looking at electrophilic addition, and we'll do a wee bit of a recap on the mechanism of that we saw in our previous videos. But in this lesson we're going to have a look at what happens when we have an unsymmetrical alkene and how that can lead to a couple of different products. So just before we move on, just a quick recap of what we did in our last lesson, and if you need to have a look over that and your notes, please do that before moving on, just so that you're familiar with this mechanism, because I'm going to assume that you're confident with that when addressing this part of the topic. So we looked at the electrophilic addition of alkenes, and with all of our examples we just used ethene. It's the easiest one to show the mechanism of. There's not too much going on in that molecule, and also it's symmetrical. And that just simply means that the double bond is essentially in the centre of the molecule, and the chain looks the same either side of the double bond. And we'll have a look at examples now where it's not symmetrical, and you'll see hopefully what I mean by that. And so here on the screen you have the example of hydrogen bromide reacting with ethene. And just a reminder of what happens in this mechanism. Remember that a pair of electrons from the carbon-carbon double bond, the pi electrons, so from the pi bond of the double bond, so that pair of electrons jumps out, essentially forms a bond with the delta positive end or the fully positive end of your electrophile. In this case was hydrogen. So it forms a bond with the hydrogen. As a result, the hydrogen has to break its bond with bromine. And so those two things happen in the first step. Then what happens is one of the hydrogens, we're at the second stage here, and one of the hydrogens has formed a bond with one of the carbons, leaving a carbocation, so a positively charged carbon ion, and our bromide ion. The bromide ion then uses its lone pair of electrons to form a bond with the positively charged carbon, and then we end up with bromoethane. So what has happened, you can see our hydrogen bromide has added across the double bond. So there's no longer a double bond between the carbon atoms, but a single bond. And hydrogen has added to one of those carbon atoms, bromine has added to the other one. And with this example, it didn't really matter which way round we did it. It didn't matter which carbon the hydrogen went to and which carbon the bromine went to. But in some cases it does matter. So where it matters is if the alkene is unsymmetrical. In other words, the carbon-carbon double bond is not in the middle of the molecule. So it doesn't look the same if we look left of the double bond and right of the double bond in that carbon chain. So let's have a look at the example of the addition of hydrogen chloride to propane. So propane has the formula C3H6. And you can see it doesn't really matter which way around you draw your double bond, it'll be between carbon 1 and carbon 2. And propane is unsymmetrical in the sense that if I was to put a mirror down the carbon double bond, it doesn't appear the same on both sides. Here you've got a hydrogen atom, and here you've got a methyl group. And so therefore this is not a symmetrical alkene. A symmetrical alkene will have the carbon-carbon double bond in the middle of the chain, and the chain either side of the double bond will be identical. And as a result of this molecule being unsymmetrical, when we have hydrogen chloride reacting with this molecule, when the hydrogen chloride molecule is adding across the double bond, there's a choice as to where the hydrogen goes and as to where the chloride goes. So if you remember the first step of the mechanism, what happens is your electrophile approaches the carbon-carbon double bond, because it's a region of high electron density, and the delta positive end of your electrophile will be attracted to that. So the first thing that happens is a pair of electrons from your double bond, the pi bond, will come out and form a bond with the hydrogen. That causes the bond between hydrogen and chlorine to break, and that pair of electrons moves to your chloride ion. But at this stage, we then, when we were drawing our second step, drew the hydrogen attached to one of the carbons. But here there is an option. The first option is that the hydrogen could add to carbon number 1. That would leave carbon number 2 as the carbocation, and then the chloride ion would form a bond with that carbocation. And we would end up with this molecule. If we have a think about the name of this molecule, you find your longest chain. So it's 3 carbons long, so the end's going to be propane now because there's no double bond. And then we need to number our carbons. There's 1, 2, 3. You might not want to draw your line through your molecule with this. You may want to just leave it so that it's clear what the molecule is. But then we have this chloro substituent on the second carbon. So the name is 2-chloropropane. But the hydrogen could also add to the other carbon, so the second carbon. This time the hydrogen has added to carbon 2, and that leaves carbon 1 as the carbocation, and the chloride ion would form a bond with that carbon. So this time the hydrogen has added to carbon 2 and the chlorine has added to carbon 1. Let's name this molecule. Well, again, it's going to be propane because your longest chain has 3 carbons in it. Your substituent is on carbon 1 this time. So this is going to be called 1-chloropropane. So you can see we have actually formed 2 different products here, because of the option of where the hydrogen can add to initially. So which will it be? Will we form 2-chloropropane or will we form 1-chloropropane? In reality, we get a mixture of products, but there is a rule which will tell us which will be the more common molecule and which will be the major product of this reaction. But which will it be? Well, if we have a look at the bottom half of page 19, we'll see the answer. To answer this question, we need to be familiar with Markovnikov's rule. Now, you don't need to know that that's the name of this rule, but you need to understand the concept of the rule. So, Markovnikov's rule states that when an unsymmetrical alkene reacts with a hydrogen halide, the hydrogen adds to the carbon that has the greater number of hydrogen substituents. So, in other words, the greater number of hydrogen atoms attached to it. And the halogen will add to the carbon which has the fewer number of hydrogen substituents. So when we're deciding which carbon our hydrogen adds to and which carbon our halide adds to, think the hydrogen goes to the carbon that has the greater number of hydrogens, the halogen goes to the carbon that has the fewer number of hydrogen substituents. So if we have a look back at our examples from above, the carbon with the greater number of hydrogen substituents is this first carbon. So that is where the hydrogen is going to add to. And the carbon with the fewer number of hydrogen substituents will be the second carbon. You can see the first carbon has 2 hydrogens already attached to it. The second carbon only has 1 hydrogen attached to it. So the hydrogen goes to number 1. The chlorine will go to carbon 2. So you can see that actually our major product is going to be 2-chloropropane. So let's write that in at the bottom of the page. So I've just drawn propane again here, and if we write that carbon 1 has 2 hydrogens, carbon 2 has just 1 hydrogen. So what happens when propane reacts with hydrogen chloride? Well, by Markovnikov's rule, the hydrogen is going to add to carbon 1 because it has more hydrogens, it has the greater number of hydrogen substituents, and the chlorine will add to carbon 2 because it has the fewer number of hydrogen substituents, it only has 1. And so therefore this will be our major product, and its name is 2-chloropropane. But you also need to know why this is. Why is it that this is the major product and not 1-chloropropane? And we're going to have a look at that on the next page. If you're not finished writing that down, you can pause before moving on. So in order to answer that question, we need to have another look at the mechanism. So as we discussed before, the first step of the mechanism is the electrophile approaching the carbon-carbon double bond, and then a pair of electrons from the carbon-carbon double bond will be used to form a bond with the hydrogen, and that causes the hydrogen-chlorine bond to break, and that pair of electrons that formed that bond will go to the chlorine atom. So as a result of this step, the hydrogen atom of our electrophile will form a bond with one of the carbon atoms. And that leaves the other carbon of the double bond with a positive charge. We call that a carbocation. And if you need to revisit that mechanism in full, then please go back and watch the other video. But in this example, what I've done is I've drawn the hydrogen on the first carbon, leaving the second carbon with the positive charge, the carbocation. But of course, there is another option. The other option is that the hydrogen attaches to carbon number 2, and that leaves the first carbon, carbon number 1, as the carbon with the positive charge. It is the carbocation. And actually the difference between the proportion of the products, the difference of which is the major product, which is the minor product, comes at this step. It comes down to which of these carbocations, which of these carbons with a positive charge is more stable than the other. And the answer is that the carbocation on carbon number 2 is the more stable carbocation. We'll look at this in a bit more detail down in the second half of the page. But this is what we call a secondary carbocation. And it's called a secondary carbocation because it has 2 carbon atoms directly attached to the carbocation itself, the positively charged carbon. You can see that it's essentially attached to 2 CH3 groups, 2 methyl groups. And the rule is that these alkyl groups, these methyl groups, will stabilise the positive charge on the carbon, and it'll make it more stable. And therefore the reaction is more likely to proceed via this carbocation rather than the one in the second option. So let's have a look at it and how we could describe this carbocation. Well, the second carbocation, and that's the one on carbon number 1, this is what we call a primary carbocation, and that's because it is only directly attached to one carbon atom. Let's have a look here. So you can see that the carbocation is only attached to one carbon atom, and therefore there's only one alkyl group, one carbon with hydrogen groups, stabilising the positive charge of our carbocation, and therefore this primary carbocation is less stable than our secondary carbocation. So the reaction is more likely to proceed via the secondary carbocation. So let's have a think about our last step and what our final product will be. Well, in the first option up at the top, remember what we would be also having here is our chloride ion from the hydrogen chloride molecule. Remember that in this step, the electron pair from the carbon-carbon double bond was used to form a bond with the hydrogen, and as a result that hydrogen-chlorine bond broke and the electrons went to the chlorine atom, which formed a chloride ion. So what happens here is the chloride ion uses its lone pair of electrons to form a bond with the carbocation. So that's our secondary carbocation in the first option, or our primary carbocation in the second option. So what are our final products? Well, here's the first one. As you can see, the chlorine is added into our second carbon, carbon number 2. Remember, the longest chain here is 3 carbons, and the chlorine substituent is on carbon number 2. And so we call this 2-chloropropane. And this is in fact our major product. So you could write there, this is our major product. And what's our other product going to be, our minor product? Well, our hydrogen and chlorine atoms have just added the other way round. Let's think what the name of this product is. There's our longest chain. Again, it's going to end in propane. And this time our chlorine substituent is on carbon number 1. And so this is called 1-chloropropane. And this will then be our minor product. And that's because it proceeded via the primary carbocation, which is less stable than our secondary carbocation, which led to our major product. So just to summarise in a general sense, where there's sort of competition in these type of reactions for the major and minor product. That arises when the alkene is unsymmetrical. There's going to be a choice of products. So you can determine the major and the minor product by Markovnikov's rule, and the fact that the hydrogen will add to the carbon with more hydrogen atoms attached to it, and the halide ion will attach to the carbon with fewer number of hydrogens attached to it. So that's how you can sort of quickly determine the products, but in terms of explaining it, it all depends on how your mechanism proceeds and what carbocation is formed as a result. And what you need to remember is that essentially a tertiary carbocation, which is a carbocation which has 3 carbon atoms directly bonded to it, is going to be more stable than a secondary carbocation, which is a carbocation which has 2 carbon atoms directly attached to it. And that's going to be in turn more stable than a primary carbocation, which has 1 carbon atom directly attached to it. And that's because the alkyl groups that essentially are the carbon atoms directly attached to it. So for example, methyl or ethyl, or it could be a branched alkyl group. Those stabilise a carbocation by donating electron density towards the positively charged carbon, and therefore it is less charged effectively overall. If you've got electrons which are negatively charged being donated towards that positive charge, then it is essentially stabilising or cancelling out some of that positive charge. Therefore it's more stable, and therefore the reaction is more likely to proceed that way through the more stable carbocation. And as a result, as it says down here, reactions will favour the formation of a tertiary carbocation over a secondary, and in turn over a primary carbocation. Down at the bottom of the page, I've drawn a tertiary carbocation that's sometimes given the abbreviation 3 with a little circle in the top right hand corner, a bit like degrees, so almost like 3 degrees. And you can see that the carbocation, the positively charged carbon, is attached directly to 3 other carbon atoms. Those in turn will be either methyl groups or ethyl groups or whatever. They will have hydrogens or carbons attached to them. But if we just look directly at what's attached to the carbocation, and what will happen is these groups, the carbons with the, methyl or ethyl or whatever, and they happen to be these alkyl groups, will donate electron density towards the carbocation. In other words, stabilising that positive charge. Therefore, this carbocation is quite stable. That's going to be more stable than a secondary carbocation. A secondary carbocation has only 2 carbon atoms directly attached to it. So those 2 alkyl groups will donate electron density towards the carbocation and will stabilise it, but not to the same extent as the tertiary, because the hydrogen atom that will be there in the secondary carbocation compared to the carbon, the third carbon of the tertiary carbocation, the hydrogen has no ability to donate electron density towards the carbon, and therefore doesn't have any effective stabilising on the carbocation. So the secondary carbocation is less stable than the tertiary. And a primary carbocation will only have 1 carbon atom, 1 alkyl group directly attached to it. And so that group will donate electron density towards the carbocation, but obviously the stabilising effect will be less so than the secondary and tertiary in turn, because it only has 1 of these alkyl groups donating electron density and stabilising the carbocation. So primary carbocations are the least stable, followed by secondary carbocations, followed by tertiary carbocations. And so when determining the preference of product, it's going to be the mechanisms that proceed by the tertiary carbocation first, leading to your major products, followed by secondary carbocations would be the next most stable, followed by the primary carbocation mechanisms, which lead to your minor product. So when judging this, just look at your starting alkene. If it's unsymmetrical, you know that there's going to be a mixture of products, and your major product will be the one that proceeds by your most stable carbocation. So over on page 21, you have another example. It asks you to predict the major product of the reaction of pent-1-ene with hydrogen bromide, and asks you to draw the mechanism for this reaction. So the structure of pent-1-ene will look like this. So 5 carbons in your chain, and pent-1-ene means that the double bond is between carbon 1 and carbon 2. You can see that this group on one of the carbons of the carbon-carbon double bond has the formula C3H7. So what is sometimes easier to do is to draw the alkene like this. Just it will then take up less room in your mechanism. So what I'd like you to do is to pause the video now and to give this a go. You don't have to do it in the order of the question. In other words, it says predict the major product and then draw the mechanism. You can draw the mechanism as you go and then essentially determine your major product from that. Just think about Markovnikov's rule, which carbon is your hydrogen going to add to? The hydrogen of the hydrogen bromide. And then which carbon is the bromine going to add to? And as a result, what is going to be the structure essentially of your carbocation, and you can use that essentially as an explanation of why you get the major product that you do. So pause the video now, give that a go, and then you can play the video again to check your answer. So the first step of your mechanism will be as follows. You want to draw a curly arrow coming out from your carbon-carbon double bond to represent that bond breaking, and the pair of electrons from the pi bond of your carbon-carbon double bond being used to form a bond with the hydrogen. As a result, the hydrogen-bromine bond will break and that pair of electrons will go to the bromine. So which carbon will your hydrogen add to? Well, by Markovnikov's rule, it will add to the carbon with more hydrogen substituents. And the reason why that's the rule is because what that ends up with is the positive charge sitting on the carbon with less hydrogens on it. Essentially the carbon that's going to have more alkyl groups attached to it. And so you can see the carbocation. The intermediate product is the one that's shown on the screen here, and you can see that this is a secondary carbocation and it is more stable. If we had put the hydrogen on the other carbon, in other words carbon number 1, it was attached to 2 hydrogen atoms and then the rest of the carbon chain, so it would have been a primary carbocation, which we have learned is less stable than a secondary carbocation. What happens next then? Well, the bromide ion uses its lone pair of electrons to form a bond with the carbon that is positively charged at the minute. And this should be your final answer, your final product. Let's think about the name then. Well, the longest chain has 5 carbons in it, so the end's going to be pentane because there's no longer a double bond, so it's not pentene anymore, it's pentane. That's the end of the name. Then we need to number our carbons so that the substituent, which is our bromo group, is on the lowest possible carbon. So we're going to start here. That'll be 1, 2, and then these will be 3, 4, and 5. I know we've grouped them together as C3H7, but that'll be carbon 3, 4, and 5. So this is therefore called 2-bromopentane. That is your major product. You will also get a bit of 1-bromopentane, but that will be your minor product. And so when doing these, you can draw out both options and see which is going to be my secondary carbocation, which is going to be my primary carbocation. But you can predict that through Markovnikov's rule. In other words, the hydrogen adding to the carbon that originally has more hydrogens attached to it. And then use the stability of the carbocation to explain your major or minor products. If you'd like a bit more practice with this in determining what will be your major product and even drawing the mechanisms for these and even writing an explanation of why the major product is what it is, then you could try the following examples. So but-1-ene with HCl, 2-methylpropene with HBr, or 2-methyl-but-2-ene with HCl. So if you want more practice, pause the video and write those examples down, and you can either try just predicting the major product or also drawing the mechanism as well, and also if you want writing an explanation of why the major product is what it is, and then I'll write those answers out and put them with the completed notes. So I'd just like to briefly explain what I'd like you to do for the rest of the topic. Essentially, the rest of the topic you met at GCSE, you've met all of the remainder of the reactions. So what's left to look at is the hydrogenation of alkenes. So in other words, the reaction of alkenes with hydrogen. This is an important industrial reaction, as are the other two. So the reaction of ethane with steam to produce ethanol, and the polymerization of alkenes. And I've just written the page references for you there. But because you've met all of these reactions before, the only other details may be things like catalysts, temperatures, conditions, which if you were preparing for your Unit 2 exam, you would need to learn off by heart. But you don't need to necessarily do that at this stage. Some of these reactions you'll meet again in our later topics. So I'd like you to just work through the rest of this booklet essentially using the completed notes on Teams, because you have met all of these reactions before and there's no new mechanisms or anything like that in it. But if there's anything you're not sure about, please let me know, and I can make a little video on to explain to you, or I can just answer your question by email, whatever is more helpful. Then in terms of completing the booklet, you have the option of completing the questions at the back of the booklet. It's not necessary for you to complete all of these questions, but if you would like to kind of further your understanding of this topic, then you can do so. So work your way through the rest of the topic with the completed notes. And again, let me know if you have any questions. So all that's left to say is well done for making it to the end of alkenes after you've completed this booklet, of course. And so that means we have now completed 2 of our organic families. We have completed alkenes and we have completed alkenes. And coming next is halogenoalkanes.